What if everything you learned about atoms back in school was actually only half the story? You know, if you're picturing that classic textbook drawing, a tiny, dense nucleus with little electrons whizzing around it in perfect circles, kind of like miniature planets orbiting the sun, you are definitely not alone. It's a completely iconic image. But as we're going to see in this explainer, quantum physics reveals a reality that is just far more mysterious, highly complex, and honestly, completely different from that neat little solar system model. So consider this massive paradigm shift. What if electrons don't orbit the nucleus like miniature planets at all? I mean, it completely turns our everyday intuition upside down, right? According to modern quantum physics, electrons simply do not travel in tiny, fixed circular paths. The whole idea of a miniature solar system existing inside every single atom is actually a pretty major misconception. To really grasp how the universe truly works on a microscopic scale, we literally have to throw away those rigid circular tracks and start thinking in a completely different way. Now you might be thinking, well, didn't those early scientific models work? And yes, they worked wonderfully for the absolute simplest elements, like a basic hydrogen atom. But physicists quickly realized they had a massive problem on their hands. As soon as things got even slightly bigger, the planetary model completely broke down. It failed to explain complex atomic spectra, the actual mechanics of how chemical bonding works, or the totally unpredictable behavior of multi-electron atoms. Scientists discovered that electrons behave way more like waves than tiny solid planets moving in a straight line. Basically, the old reliable rules of classical physics just didn't apply to the messy reality of complex chemistry. If we trace this evolution from classical physics to a total quantum revolution, we start back in 1913. That's when Niels Bohr proposed those fixed, circular electron orbits. And don't get me wrong, this was a brilliant leap forward at the time. But as we move into the 1920s, scientists were actively studying larger atoms and realizing the Bohr model was just failing spectacularly. The math simply wasn't lining up. Then, in the late 1920s, everything changes. Erwin Schrödinger introduces his famous equation, bringing wave behavior into the spotlight and giving us a completely, entirely new picture of the atom.
The fundamental difference here really comes down to one key thing: certainty versus probability. Think of a classical orbit, like a planet around the sun. It has a fixed path, an exact trajectory, and you have complete certainty about where it is and where it's going. In stark contrast, quantum mechanics introduces the orbital. There is absolutely no exact path anymore. Instead, it's this strange, fuzzy probability cloud where we only know the likelihood of finding an electron in a given space.
So, to put it simply, an atomic orbital is formally defined as a three-dimensional region around the nucleus where there is a high probability of finding an electron. Imagine you spray a bottle of perfume into a room. That perfume doesn't travel in a single, perfectly straight, predictable line, does it? No, it spreads out into a mist, into a cloud. Electrons behave in a surprisingly similar way. Instead of following precise tracks, they exist as these probability clouds. The brighter and denser the area of that cloud, well, the greater the chance of detecting the electron right there at that very moment. And this is where the math gets absolutely beautiful. It perfectly matched experimental observations where classical physics had just completely face-planted. When Schrödinger solved his incredible equation, the allowed solutions for the electrons weren't neat two-dimensional circles. Actually, scratch that. They were nothing like circles. They were unique, three-dimensional standing wave patterns, each possessing its own specific energy and shape. Quantum mechanics had succeeded by mapping out these complex wave patterns, finally giving scientists a model that perfectly aligned with reality.
These invisible shapes basically fall into four fundamental categories: S, P, D, and F orbitals, and they act as the literal scaffolding for all chemical elements. First up is the s orbital. It's perfectly spherical, the absolute simplest type, and it's where every single atom begins filling its electrons. Next, we get the p orbitals. These look kind of like dumbbells, putting along the x, y, and z axes, which is actually what creates the directional nature of chemical bonds. Then we have the d orbitals, mostly shaped like four-leaf clovers, which beautifully explain the fascinating properties of transition metals. Think iron, copper, and gold. Finally, the most complex are the f orbitals, featuring 7 different crazy shapes found mainly in rare earth elements, giving them incredibly unique magnetic and optical properties.
Now you might be wondering, okay, so what? Why does this actually matter to me? Well, orbitals aren't just abstract math for physicists to argue about.
They literally build our tangible world. They determine exactly how atoms bond together and dictate the specific physical shapes that molecules take. I mean, they are the underlying reason why carbon can form the incredibly complex structures that serve as the basis for all life on Earth. They cause oxygen to react with hydrogen to form the water we drink. They explain why metals conduct electricity, dictate why a diamond is incredibly hard while graphite is soft enough to write with, and they even provide the specific quantum states necessary for the structure of your very DNA to exist.
But it goes way beyond just the natural world. Understanding these probability clouds has completely transformed human science and engineering. Technologies like semiconductors, solar cells capturing energy from the sun, LEDs, lasers, life-saving MRI scanners in hospitals, cutting-edge quantum computers, nanotechnology, the whole shebang. They are all powered by our mastery of orbitals. Modern electronics and the devices you use every single day, literally the smartphone in your pocket or the screen you're looking at right now, simply would not exist without this deep understanding of the quantum states within atoms.
To wrap up this explainer, I want to leave you with this final thought. Everything you see is shaped by orbitals you can never directly observe, yet they define the very fabric of reality. It's pretty incredible to think about. The next time you look around your room, take a walk outside, or even just look at your own hands, remember that every single material and living organism is built upon these invisible, shifting quantum structures that defy our everyday intuition. So, I'll leave you with this. If the solid, tangible world around us is entirely constructed from clouds of mathematical probability, how much of our